Welcome. This screencast is going to review the gas laws and specifically how they relate to stoichiometry. So often we measure the mass of samples in the lab and convert between moles and mass, and this works really well with solids. But with gases, remember, kinetic theory says gas particles have lots of space between them and minimal of any interparticle forces, which means most of a gas's volume is empty space, which means gases are very, very light. So mass may not be our easiest or best measure. In fact, Avogadro realized equal volumes of all gases at the same temperature and pressure contain an equal number of particles. So this can make things much easier for us. For example, 40 cubic centimeters of carbon monoxide and 40 cubic centimeters of oxygen should react to form how much carbon dioxide if all gases were kept at the same temperature and pressure. To do a problem like this, we don't need to measure the mass. In fact, we don't even need to convert from the 40 centimeters cubed. We can write the balanced equation. We can determine the limiting reactant out of those two using the volume ratios. And then we can determine the volume of CO2 produced. So here's my example, and my balanced equation says 2CO plus O2 will give me 2CO2. And if I look at my equation says I need 2 moles to 1 mole to yield 2 moles, or I can think of that as volume because equal volumes of gases have equal number of particles under the same conditions. So this is really 2 liters of CO plus 1 liter of O2 gives me 2 liters of CO2. So we see there's a 1-to-1 ratio with CO2 and CO, but there's a 1-to-1/2 or 1-to-2 ratio or 1/2 ratio between the oxygen and the CO2. So we should expect 20 centimeters cubed of CO2 to form from our oxygen, whereas we'd get 40 centimeters from the CO. So we are only going to get 20 cubic centimeters because oxygen's our limiting reactant. Here's another example. When 10 centimeters cubed of a hydrocarbon burns with excess oxygen, 30 centimeters cubed of carbon dioxide and 30 centimeters cubed of water vapor are produced. So what is the hydrocarbon? Well, if we look at this, I've got CXHY representing my hydrocarbon because I don't know what those subscripts are, but I do know there's 10 centimeters cubed of it. I've got O2 has to be my other reactant, and I've got an excess of that, so I don't have to worry about that coefficient. And then I know I'm going to produce 30 centimeters cubed of CO2 and 30 centimeters cubed of H2O. So what I see is that both of the products have a 3-to-1 ratio with the hydrocarbon. So that means there'd have to be 3 carbons and then 3 times 2 or 6 hydrogens in the unknown. So my unknown must be C3H6. Molar volume then relates to this idea or principle that Avogadro came up. It's very similar to molar mass, but it's the volume that 1 mole of gas occupies. And since gases are highly reactive to the conditions, the temperature and pressure, it would be the volume of 1 mole of gas, of any gas, measured under the same conditions. And we say it's 1 mole of any gas because under the same conditions, any gas would occupy that same volume. But molar mass definitely changes with the kind of atoms present, whereas molar volume won't. So just like with molar volume, we can calculate the moles of gas there. Our moles of gas should be equal to the volume of the sample divided by the molar volume. And a couple equalities or conversion factors that we'll use frequently is, remember, at STP, standard temperature and pressure, so 0 Celsius and 1 atmosphere, then the molar volume is 22.7 liters per mole for any gas. And at RTP, that's room temperature, 25 degrees Celsius and 1 atmosphere. Then it goes up slightly to 24 liters per mole, or as IB likes to say, decimeters cubed moles minus 1. So just get used to that label. So the metric system and units of measure, let's just review a little bit here. The metric unit for length is meter, and the metric unit for volume is liter. But they have a very cool relationship. It was deliberately established that since length times width times height is one way to find volume, then any length measurement cubed also represents volume. So when the liter was defined, it was set up to equal 1 decimeter cubed. So you will often see an IB or metric using societies that dm cubed is used instead of liter. And that also means 1 centimeter cubed, or 1 cc, is equal to 1 milliliter. So here's another example for you. What volume of oxygen at STP is needed to completely combust 1 mole of butane? So first of all, I need my balanced equation, which I have. And then I look at my molar ratio, and I see 1 mole of butane has a 13:2 relationship. 13 moles of oxygen per 2 moles of butane. I notice my butane's missing the last part of its formula here. So the 13:2 ratio means it would be 6.5 moles of oxygen. And then as far as what volume that is, because it's at STP, I can go ahead and multiply by the 22.7 and get 148 liters or decimeters cubed. What volume would 0.0200 grams of helium occupy at STP? So I have to go ahead and convert my helium into moles. And once I have my moles, because it's at RTP, I can multiply by the 24 liters per mole. And I see that 0.02 grams of helium would occupy 0.132 liters or decimeters cubed. The ideal gas law comes from kinetic theory describing gases being mostly empty space with the free-moving particles of negligible volume and no intermolecular forces. That whole idea leads to this concept of an ideal gas. And most gases behave pretty much like an ideal gas most of the time. And so we can predict their behavior with the gas laws. And there's 3 individual gas laws that then get combined into the combined gas law, as well as the ideal gas law, which I'm just going to quickly review for the rest of this video here. I also want to point out there's 2 conditions under which real gases tend to deviate or not behave ideally. And that's when the temperature gets extremely low and or the pressure gets extremely high. And if you think about it, under either of those conditions, the gases are going to be moving much closer together, becoming getting much closer to that phase change of becoming a liquid. And so as the particles move closer together, now that negligible volume is going to become noticeable because the space between the particles is decreasing. And that intermolecular force that didn't come into play before, now suddenly the particles are going to start having some effect on each other. So that's why low temperature and high volume will cause gases to deviate. And you can correct the ideal gas law for this. Van der Waal came up with a correction, but fortunately for us, we don't have to deal with that. So the gas laws, just a couple reminders on units. The units of temperature must be in Kelvin because 0 Kelvin is absolute zero. It represents no kinetic energy or movement of particles, whereas Celsius has negative temperatures available and negative energy really isn't possible. The interval amount of energy 1 degree Celsius and 1 Kelvin represents is exactly the same. So the conversion's easy. You just add 273 to your Celsius temperature to get Kelvin, or subtract 273. Units of pressure also vary according to the instrument being used, and different countries have different units they tend to use, but the official SI or metric unit is Pascal, although kilopascal is more commonly used because Pascal is a fairly small unit. But get used to seeing Pascal and kilopascals, and the metric unit for volume is liter or decimeters cubed. So the individual gas laws, Boyle's law is looking at pressure and volume. Remember, it's an inverse relationship, so if one increases, the other decreases. So P times V is a constant, or we get P1 times V1 equals P2 times V2. Charles's law looks at temperature and volume, and they have a direct relationship, meaning when one increases, the other increases, so they increase and decrease together. So V over T is a constant, or V1 over T1 equals V2 over T2. And the temperature and pressure relationship is also a direct relationship, so they increase and decrease together, so P over T is a constant. And we end up with the combined gas law that if you are looking at all 3 or allowing changes to all 3, then P1 times V1 over T1 equals P2 times V2 over T2. And then finally, the ideal gas law comes from the combined gas law, because the combined gas law can really be thought of as P times V over T equals a constant. So in the ideal gas law, R represents that constant, and the fourth variable, moles of gas, or N, is also included. Just a warning that the IB data booklet only gives you one value for R, 8.31 joules per Kelvin per mole, where pressure must be in pascals, not kilopascals, and volume must be in meters cubed, not decimeters cubed, so not a liter. So if kilopascals are given, you can divide the constant by 1,000, which you're used to seeing 0.00831. That's because kilopascals were used. Or if liters are given, you can, this should actually say multiply by 1,000. So make sure you correct that. I made a few mistakes in here, but you can multiply by 1,000 if decimeters cubed are given to get to meters cubed.